Hey friends, welcome to our weekly Data Talk, a show where we talk with data science leaders from around the world. Super excited to have Ameen Kazaruni back. This is episode 2 with Ameen. Had a great chat with him last time about machine learning and e-commerce, and he's back with a fascinating new topic, talking about genetic algorithms in the changing e-commerce ecosystem. And before we got on, Ameen was kind of sharing a little bit about what he means by all this. So, I mean, can you kind of give me, because I have no idea about what genetic algorithms are, how they're being used, how you're using them. So can you kind of give like an introduction to what you mean?
Yeah. So first off, thanks for having me back. It's great to be here chatting with you again. And I think it's cool, like the evolution, because we spoke about machine learning and e-commerce first, and now I kind of want to talk about genetic algorithms in e-commerce because we've had a lot of luck using them, and they're an exciting new field, right? So I don't want to say it's a new field of machine learning because it's technically not, but we're using it in data science. So I think that's safe to say that it is being used as a tool in your data science toolkit, but it's not traditional machine learning. So I think a good way to jump into genetic algorithms is first to kind of a quick refresher on how we're like defining machine learning and like deep learning and stuff like that.
That'd be great. I mean, I need it.
No, it's just to like draw the kind of line.
I need all the help I can get here.
So machine learning, you got your traditional, you got your supervised and unsupervised learning. And I'm gonna take this watch off because it keeps vibrating. But you got supervised and unsupervised learning. And in supervised, you got your classification, you got your regression techniques, but you're effectively trying to predict something, right? Like it's predictive modeling, or you're trying to kind of do a clustering problem where you don't know exactly what the labels are, but you're grouping things together, right? But genetic algorithms are a kind of optimization solution. So effectively, think of genetic algorithms as looking at a population of potential solutions to a problem, and then kind of trying to find the best one. So it's not actually predicting something, it is optimizing a solution space effectively to get the highest quality solution. So that still sounds like a bunch of probably. Can I just grab the paper and come over there?
Oh, this is fascinating.
Yeah, thank you. So a genetic. So let's talk a little bit about what the evolutionary process is in general, right? So there's two primary principles in the evolutionary process that are kind of leveraged in a genetic algorithm. One, the traits of a parent will follow on to the children. So like you look at Mendel's biological experiments, you got wrinkly peas and smooth peas making children. You're going to get some wrinkly peas, some smooth peas. You got wrinkly and wrinkly, you're going to get wrinkly children. Those experiments showed us that traits from the parents carry down in future generations. And then Darwin's theories of like survival of the fittest, which ironically, I don't think he ever said. I think an economist said that, but that's the point. But Darwin's principles were, the more capable you are of surviving, the more likely you are to reproduce. So effectively, the two tenets we have here is any individual that is the fittest at whatever objective function, which in biology is just survival, is more likely to reproduce. And if you're more likely to reproduce, those traits that made you fitter are more likely to carry on into your children. So that's simple principles of evolution, right? So this guy, Holland, decided, let's make an algorithm that does the same thing.
Really?
So it's very cool. You've got a solution that's represented as like a series of binary bits, right? So let's say we've got an algorithm that just looks like this, right?
Okay.
So let's define a very simple problem. We've got the knapsack problem, which is one of the most researched mathematical problems that exist, which is I've got a bag that can hold 20 pounds, and then I've got like 6 books, okay? What is the maximum number of books I can fit in this bag, right? It seems simple because as a human being, you can quickly figure it out, but how do you get a computer to nail that problem, right? And this is a similar land in which like traveling salesman lives, right? A salesman needs to visit 50 cities. What is the best order in which he should visit the cities, right? So these are all optimization problems. So let's go back to this piece of paper right here. If you look at this, every position that's a 1 implies that that book is in the bag. If it's 0, it means the book's not in the bag. So this is one potential solution, right? The fitness function is the number of books. But if the weight goes over 20 pounds, which is the maximum the bag can hold, we change it to 0, right? So now imagine we've got another solution that is effectively this, which is a different solution. We're going to sum these up and look at which is a better solution, right? But if they're both good solutions, we're going to follow simple principles of like genetic crossover and have them mate with each other and like create a new solution that looks like this. And now we've got
I love this. I mean, this is like the first time we've had like code on Post-it notes. This is awesome.
I racked my brains last night figuring out how we're going to talk about
I love it. I love this.
Children, and I'm like, I'm going to use this. That's the only way to do it. Potential solution that came from 2 good parents may actually be a better solution than either of the original solutions was.
Oh.
This just keeps continuing. And these are the basic tenets of a genetic algorithm, right? You initialize a population of solutions for whatever problem you have. Then you evaluate how good each one is. So that's the evaluation phase. Then you've got your selection phase, which based off of how fit they were, you pick a group of parents that are going to be able to reproduce, fit parents, and you then do crossovers just like we did with the Post-its, where we take the pink parent and the yellow parent and we make this new child over here, right? And we create a whole new population of potential solutions. And then we evaluate them again. And if that generation is better than the previous generation and has a fitter solution in it, we have some stop criteria, right? We're like, oh, this solution is now good enough. I only wanted to, out of the books that I had, fit at least 4. I found a solution where 4 books fit in the bag. Let's stop. Those are the 4 books. Put them in the bag and let's go, right? So the good thing about a genetic algorithm is it's not going to give you the best solution. It's going to give you a good solution and an approximately close enough answer, right? So that's pretty much it. That's how genetic algorithms kind of work. So they've got the initialization, the evaluation, the selection, which effectively decides who's reproducing, which amplifies good traits, and then you just keep going in this cycle.
That is brilliant. I am more confused, unfortunately, but the data scientists that are listening in, they got it. They got it. I'm sitting here going, I just love the fact that you made Post-it notes for all this. So for those that are listening to the podcast, you got to watch the video now to see Ameen with all these amazing Post-it notes.
Okay. All right.
No, this is great. So, so can you maybe give me like kind of a practical example of how this might look with a model?
Sure. Yeah. So let's use an example of like, so a place that we have experimented with it potentially is like in search, right? Because genetic algorithms are effectively a family of search and optimization algorithms, right? So let's say that, let's step back. Let's make it a little easier. We've got customers that shop on a website, let's say, and you want to figure out what properties this customer is passionate about, right? So there's different things that I can do on a website as a person. I can do a search, I can go to a product page, I can add something to my favorites, or I can add something to my cart, or I can buy something, right? Now, each one of these interactions shows a different affinity to that product. So if I just look at a running shoe, or if I just look at a boot, right? Versus if I actually add a boot to my cart, it shows different affinity that I may have towards a boot, right? Yeah. So if it is a simple classification problem of is Ameen going to buy a boot or not, you could just use machine learning, right? Where you just build an algorithm. Okay, he looked at a boot these many times, he clicked on a boot these many times, he added a boot to cart these many times, and that's that, right?
Yeah.
And then predict yes or no he's going to buy a boot. What's the probability of him buying a boot? But what we want to do is we want to figure out, okay, how important are boots to Ameen? Because we also want to know how important running shoes are to Ameen. We also want to know how important sneakers and athletic shoes are to Ameen. And based off all these importance criteria that we've identified, we kind of want to build features that personalize for Ameen, right? So now a genetic algorithm is a good potential solution because those weights that are going to be associated to each action can be determined by a genetic algorithm. Now, obviously, the piece that I can't share is the fitness function, which is critical. At each population stage, you evaluate a fitness of a potential solution to see how good it is. And that fitness is your secret sauce, because that fitness is what you're trying to optimize. And when you define and design a good fitness function, you actually find the perfect weights that tell you how important each item is to each one of your customers. So what's really cool about genetic algorithms is that they're constantly running, so they're constantly adaptive. So when you think about e-commerce, right, it's a constantly changing ecosystem, right? You're constantly acquiring new customers. You are, customers start behaving differently as they've been customers longer because they become loyal. And then towards the end of a customer's life cycle, they start behaving differently as well. So you've got like a mixed bag of customers constantly that your customer base.
And it's constantly changing too, because like interests change, right? Families grow, all that.
That's a good one, right? Families grow, more people. A lot of people aren't shopping. Like, your kid doesn't have their own account, right? Or sometimes families just shop in the same account. So family sizes are changing. And more importantly, you've got inventory, right? Your inventory is changing. We may not have something in stock. We may not have anything in stock. And then in addition to that, you've got seasonality. Like in the summer, you're buying different kinds of product than you're doing in the winter. Or like when fidget spinners went crazy. Nobody knew spinners were going to go crazy, right? How do you react to those kind of sudden changes in your ecosystem that are like time-based, inventory-based, customer-based? Honestly, there's no good answer, right? You're constantly retraining new machine learning algorithms to react to these changing ecosystem. You're repeatedly having to have, this is my summer model. This is my winter model. People buy winter jackets in the winter while people buy sandals in the summer. But these are all trends that we know about. Like, we know that this is going to happen every time right before people go back to school. People are going to buy products. So you'll see back to school sales over all websites, right? But that's what we know is going to happen. What about the trends or the changes in the ecosystem that we are not aware of, that we've not labeled or given a name like back to school to, right? How do you react to that? Like, how do you know to build a different algorithm for that? You really don't. And that's where genetic algorithms are super helpful, because they adapt to the ecosystem. So what is potentially a good candidate solution today may not be the best solution 3 months from now or a quarter from now. And it will tell us that. And we actually have systems that will automatically deploy those changes and use the search results or, features accordingly.
That is brilliant, amazing. So, I mean, where do you see genetic algorithms mostly used right now?
So right now, today, genetic algorithms are being used across the board so there's a popular part of, again, taking it back to machine learning a little bit, there's a very important step in machine learning that is known as hyperparameter tuning. And I'm sure at some point in this podcast, someone has spoken about hyperparameter tuning, because it's a critical aspect of machine learning, right? An algorithm does a certain task, but then the rate at which it learns or the speed at which it does something or the activation function a neural net uses, these are all hyperparameters that need to be tuned. And the performance can swing from like 70% accuracy to 90% accuracy with the exact same algorithm, just with hyperparameters being tuned differently, right? So the hyperparameter space can be thought of as a potential space that a genetic algorithm can search through. So right now, a lot of people do like random searches to look for the ideal set of hyperparameters for a machine learning algorithm. But more and more, we are seeing in industry, people start using genetic algorithms as an alternative to random search or grid search in hyperparameter tuning, because it just seems more intelligent and faster at searching through this large dimensional space, which has a non-obvious solution. So we see a lot of that in industry right now. Other than that, genetic algorithms are very useful in like hardware design, because when you're designing an example of where they're used very often is wings of planes in industry are designed using genetic algorithms very often.
Really?
Because like there's tiny details that, and I'm obviously not a wing engineer, so I can say this tiny detail.
I bet you could though if you wanted to.
So I can't name any of the tiny details that are important. But what I can tell you is that there's enough. I mean, you go back to the Post-its, which I'm not going to throw up right now. There's audio listeners as well. But if you've got, let's say we've got 5 things that can change in a wing design, right? And some combination of those 5 things being present or not present is the ideal design for a wing. It's not usually 5. It's normally hundreds or thousands, right? So it's completely non-obvious which one should exist and which one should not exist in a design. And some of them existing together could be a wing that's a circle, which doesn't work. Some of them could just be a wing that's facing this way, forwards, which won't work. And some of them are like the perfect wing, which gives you the best aerodynamics, right? So a genetic algorithm allows you to try out all these potential solutions, which brings me to an interesting point. In genetic algorithms, you have a lot of bad solutions. And you can actually send a plane up in the air with a wing that may fail because the plane crashes. And that's not
right.
So very often, genetic algorithms, when your fitness function needs to be a simulation. So let's say you're even doing it on let's say I was like changing the way products looked on the website using a genetic algorithm completely, right? Yeah. I couldn't risk a horrible solution going out on the website because now it's going to make no sense, right? Or I was like trying to find the best fidget spinner design, and there were some designs where the fidget spinner didn't spin. I couldn't put that out in market because that's not going to work. So that's why a fitness function becomes a little difficult because you can't directly get the feedback loop of, did it do the thing I wanted it to do? Because when it doesn't do the thing you want it to do, you could lose a lot of equity, a lot of investment, or whatever you're trying to optimize for, right? So simulating fitness functions becomes a very important part of designing a genetic algorithm because you got to design a fitness function that is a good proxy for reality. So you have a solution that works the same way out in the wild as it does on your fitness function. So that's like kind of an important aspect. Like I'm trying to think of an example now. Let's go back to the wing design, right? Let's say we had wings we had a huge airplane, and one of the features were the ratio of how big the wings were to the airplane. And let's say it was like, they need to be super tiny. So imagine a full-sized airplane with wings the size of a Oreo sticking out on either side of them, right? That plane's not going to fly, and you don't want to try and make that plane fly. But then how do you know that a small ratio is bad if you don't actually see it fail? And that's where like simulations are important. But the simulation needs to be a good proxy for reality because now you're trusting that the design that worked on the simulation is something that can actually successfully fly. So you're going to put that in the air. So you need to make sure your simulations are well designed and actually representative of the thing you're trying to optimize or minimize.
Can you talk about e-commerce? Because I loved your example about how traditionally, like with machine learning, like you see my behavior on whatever website, and let's just say shoes, and I love Converse, and so you know that I'm always looking at different colored Converse, and that's in my history. I'm looking at lots of different Converse, and so you have all these data points about me that I definitely like Converse shoes. I'm checking out shoes all the time. I put them in my shopping cart. Sometimes I don't buy anything, but they're just there. So you're collecting all this data, and so you can make predictions around, Mike's probably going to be interested in seeing Converse shoes when he goes to the site, and I want to make it easier for him to see the newest shoes that are coming out, the newest designs. He's interested in that content. How would a genetic algorithm work differently or work with current machine learning predictions on type of content? You know what I'm saying?
Yeah. So let's jump into a couple of like hypothetical spaces, right? Let's say we've got me. Let's use me as an example, and like that, and I know that I like. And let's forget the shopping experience completely. Let's use my own brain, and my own brain knows that I like North Face jackets, right?
Yeah.
And it's like, I love North Face jackets. I love North Face jackets. I love North Face jackets. There's a model in my head that's like, North Face jackets are the everything, right? You need North Face jackets. I'm walking down the street, and it's Vegas, and it's 110 degrees out, and I walk past the North Face store. Most likely, I'm just going to walk past it.
That's right.
And designed, if somebody put that North Face store because a machine learning algorithm told them Ameen's going to walk by and Ameen loves North Face jackets.
Yeah.
That store there, that's going to happen, but I'm going to walk right by it. And the reason is going to be that model predicted that I love North Face jackets, but it didn't know that because of the changing ecosystem, I didn't need that right now. That's where the genetic algorithm would be like, yeah, he loves North Face jackets more than anything on the planet.
Yeah.
He doesn't love Nike sandals that much, but it's really hot out, and he's most likely going to buy a sandal right now. So maybe we put a sandal store out there instead. Like, it's not how much you love something. It's about, is this the right ecosystem?
I see. Yeah. Okay. That's a really good example. I like that. Yeah, that's brilliant. I mean, so obviously you knew about this, you knew about genetic algorithms. What made you think, I want to apply that, like to bring that over?
That's a good question, because it's actually a funny story where we decided it. We were working on a solution for a problem, and we kept trying to build different algorithms to solve it. And I'm gonna kind of be a little vague here because of secret sauce. But we're working on a solution and we're trying to solve it. And every time we bump up into a problem where we had to keep increasing the complexity of the problem, where we're like, oh, let's add a couple more dimensions to it. And then one of the machine learning engineers on the team, she was sitting there and she's like, oh, you know what we should do? Let's just search. So now we have this massive set of things that we need to optimize. We've identified every problem that we bumped up against. Now let's just search through every possible value for every single one of these, and whichever one's the best, we'll just use. And she was making a joke because that's known as an NP hard problem. It is, you need to solve it by, there's, I think, $1 million or $2 million prize out there for anybody who can come up with a solution to do that, because it is a thing that cannot be solved in non-polynomial time, if I'm saying that right. So it's like, basically, you can't just, like, if I told you, here's 5,000 numbers, I've guessed 5,000 numbers, now you keep coming back to me with 5,000 numbers, and I'll tell you if you guess the same 5,000 numbers as me, right?
Okay.
That's a perfect example of where that's just not possible to do.
Yeah.
But if you wrote a genetic algorithm, you actually could get very close to guessing 5,000 numbers. And that, when she said that, we were like, both of it kind of struck at the same time, and we were like, let's just use a genetic approach. And it worked. It literally it ran for a couple of weeks, the algorithm, and it spat out a solution that worked. And that's what's cool about it. It's not very well understood as to why it works. So there is a theory out there known as the building block theory, and I will not even claim to understand the math behind it, but it's something about tiny pieces of the solution being parts of the bigger optimal solution, propagating forward as building blocks until the ideal solution is identified. And there's some math behind it, but it's heavily debated, and even experts in the field disagree with that solution. But it is currently the prevailing theory of building block schemata. But honestly, it's not very well understood why it works. But then, we don't know why neural nets. We know the math behind why neural nets work, but when I build a neural net and take it to the business side of things, I can't really explain what it's doing either, because a lot of these techniques are black box, right? That's one of the downsides. The good thing about genetic algorithms is you don't know how they work, but the end solution is very interpretable. It very blatantly tells you which features are being used and how important they are. And what's really cool about that, I was doing some research. And when I say research, I mean frantically reading up on to prepare for this, making sure I didn't get any of the words grotesquely incorrect. But I was doing and I saw that people actually started to use genetic algorithms for things like feature selection, which is another part of machine learning where people are, you've got 5,000 features and only 100 of them are really important to the thing you're trying to predict. How do you know which 100 to choose? People are actually using genetic algorithms to see which features get weighted heavily, taking those features and then building machine learning models with those features. So you see a lot of people using genetic algorithms just to enhance their machine learning. Hyperparameter tuning, feature selections, these are critical aspects of machine learning that are getting better and smarter because people are using genetic algorithms to actually optimize those aspects. So it's a pretty cool field because you can use it to enhance other fields, but you can also use it as a solution unto itself.
That's brilliant. So what's been the response as you've talked to other data scientists about using this method?
Oh, I don't even have to go as far as other data scientists. We have like intense conflict on the team itself.
What? And I'm what's going on?
Watching, so reactions pop up. I'll let you know which ones are team members. But it's not conflict as much as there's a lot of discussion, right? Because a traditional machine learning scientist doesn't like it. A person like very traditionally based in machine learning techniques is like, I don't fully, it just doesn't compute to what you're traditionally trained to think about machine learning. So, but at the same time, I think someone on my team, she went to the Grace Hopper conference recently, and she came back and she told me, man, you know, everyone's talking about genetic algorithms. Everyone's talking about using evolutionary algorithms for like hyperparameter tuning. So it's definitely picking up steam. But then last night I was Googling genetic algorithms in e-commerce for examples that I could use other than what we do here. And a talk that I'd given on genetic algorithms in e-commerce was one of the top results. So, and that's not because the talk was good. It was because no one's really doing it that much. So it's hard. It's hard to get opinions, right? Because it's very new. Like a lot of the literature out there is still in academia. Like in genetic algorithms in e-commerce, it's just like papers being published in an academic setting. So definitely picking up steam. And I kind of want to like, I kind of see like us as like evangelists for it because we're using it and with success. And I think they're good forms of, so this is why genetic algorithms get a bad rap, right? They're very expensive. And when I say expensive, I mean they take a long time to compute. So that fitness function that we're talking about, when that example we used about the knapsack problem, you're just adding up the number of books in the bag, right? But that fitness function can get very complex. So when you're doing hyperparameter tuning, the fitness function is actually taking those hyperparameters, building an entire neural network, and seeing how it performs. That entire process just becomes the fitness function. And then you got to do that over and over and over and over again. Now, just training a neural net's expensive. So if I came and told you, okay, now you got to go through the process of building a neural net thousands of times over thousands of generations, you're going to tell me that doesn't make sense. You know, that's the hard sell right there. That's honestly a trade-off that you need to make before you jump into genetic algorithms is the cost of repeatedly evaluating my fitness function going to be worth the time it takes for the genetic algorithm to spit out a solution? Because a popular example you hear people talk about with genetic algorithms is eventually you could write a genetic algorithm that made a monkey spit out the first 4 words of a Shakespeare play. Simply put, right? You could eventually do it. I was reading a book recently that had a cool example where if you took all the letters and words that existed in any library and then any combinations of those letters and words, it could produce every piece of text that has ever been written or ever will be written.
Whoa.
So if you think about it, any book that's ever going to be written is just a combination of words in a particular order. Right? So technically, a library has the building blocks for any book that's ever going to be written. And a genetic algorithm with enough time and with enough guessing will eventually spit out one of those. But the likelihood is 1 in a very, 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 you're more likely to win the lottery probably. And that's kind of what we're going for with genetic algorithms for smaller search spaces. So you got to really weigh those trade-offs before you go for solutions.
Well, I love the fact that you all had a healthy debate over this. I think that's so great when teams get together and can debate and debate about.
I'm just kidding. It wasn't healthy for sure.
It's good. It's so good, you know, to be challenged, to have different thoughts and different opinions about different ideas and how to approach something. And obviously it's still controversial and still going through issues, but what would be your advice for people that find themselves in a similar situation at their company? They're on a data science team. They have an idea. It's being challenged. How do you get support to push something like this through?
I think my first piece of advice for a data scientist with novel ideas who are being challenged at their company would be reach out to me on LinkedIn, and we'll be happy to talk to you. But the second advice would be, and stepping away from genetic algorithms here for a second, right? In the field of machine learning and data science, there's always different approaches and different solutions that you could try to achieve whatever you're trying to achieve, right? And you will come across machine learning scientists with a lot of different principles. Like, there'll be machine learning scientists that want to start with simple regression techniques and work their way up. There'll be machine learning scientists that will tell you, oh, let's do deep learning, fancy neural net immediately. There'll be machine learning scientists that will tell you, oh, I just read this paper from Google. It came out yesterday. We have to use it today. And there'll be machine learning scientists that kind of want to like try a little bit of everything and see what works, right? No one is wrong and no one's right. You know, the field is complex enough where you're basically taking your understanding of what models have worked on data in the past and taking that experience forward, right? You're kind of running that algorithm in your head with all the experience you've had to your best guess as to what algorithm is going to work on a new data set that you're being faced with, right? So anybody that says that, I mean, there are some things that are just wrong, but I'm talking about in the realm of what is potential. Yeah. I think healthy debate and discussion there is critical. And jokes aside, I think if that kind of healthy debate and discussion is not being encouraged, it's difficult to succeed in data science because data science is one of those fields, and corny as it sounds, there's an art to it in addition to the science that is very important because, I mean, at its core, it's intelligent approximation, right? Machine learning at its core is you cannot come up with an exact solution. So this is my best mathematical educated guess. That's what genetic algorithms, machine learning, all of it. So if your final solution is going to be a really, 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 really good guess, then it only tells you that there's got to be some debate and discussion before you come up with that solution in the first place, right? So I think it has to be encouraged, and if it's not being encouraged, you know, break out your laptop and run the algorithm you think works. Numbers speak for themselves. If the accuracy is higher and it still doesn't get used, then definitely reach out to me on LinkedIn.
I mean, one last question before we go. This has been mind-blowing for me, listening to you talk about this. What excites you about the future of how genetic algorithms could be used?
So I think what's most exciting about the future of genetic algorithms is hardware, right? We have so much aggressive progress that is happening in computational hardware that some of the blockers of genetic algorithms, which is evaluating the fitness function, is going to stop being a problem over time. Because we're going to be able to compute faster, and we're going to be able to crunch numbers faster and better, right? And that's going to put us in a position where we can evaluate more of these solutions quickly, which means that we could effectively find answers to questions that have plagued us for a very long time and optimize problems that we've not really had. Like a classic example is shipping, routing, train schedules, all these things that have no obvious solution that are currently using genetic algorithms to optimize them. You know, like which trains should run at what time, what delivery trucks, which order should they visit houses in. These are problems that are being solved every day using some other solutions and some genetic algorithms, and they don't have ideal solutions. They only have an optimal kind of this is good enough for now solution, and those are going to keep getting better and using genetic algorithms. But at the same time, I'm very excited about people starting to use genetic algorithms in fields like e-commerce, marketing, advertising, things like that. Because I recently read an article where somebody used a genetic algorithm to predict what the skyline of a city would look like 10 years from now. And that's just what the use of that is, but it's so cool. It's just so cool. Like, imagine being able to go and predict what the skyline of Vegas is going to look like 20 years from now. And it's just interesting, the problem space that opens up for solving with these kind of solutions. And I'm excited to see where that goes. Very excited to see where that goes.
That is so cool. So for those that are listening in, they want to connect with you, follow your work, conferences you're speaking at, what's the best way for them to do that?
I think LinkedIn is where I say that LinkedIn is the best way, but I'm not very good at the whole online thing, and I'm going to try and get better. But yeah,
I think you do a great job.
LinkedIn and Twitter would be my space. So it's Ameen Kazaruni on Twitter, and I think that link at the bottom should be to. Is that still LinkedIn from last time?
Perfect. Yeah. So I'm gonna So for those listening to the podcast, you can use the short URL to find Ameen's LinkedIn page is just ex.pn/Ameen, spelled AMEEN. That goes right over to his LinkedIn profile. Connect with him, follow him, and also, I believe your LinkedIn profile also has your Twitter account on there as well. So those are two great places to follow the work that Ameen's doing. And I think I might have lost him. Ameen, are you still there? I think it just froze. Well, this is actually if ever a video is going to freeze, you want it to happen at the very, very end. Although I can't say goodbye to him in person. Ameen, thank you so much for being our guest in today's Data Talk. As always, it is awesome chatting with you. My mind is always blown. I always understand like a fraction of what Ameen says, but when he gives me practical examples, I can get it. So I'm grateful for him to be our guest today, and hope to have him again back whenever he's available. To connect with Ameen, which I highly suggest that you do. Follow him on LinkedIn. He posts great content there. And again, the URL is just ex.pn/Ameen. And we'll be back next week for another Data Talk. Thanks so much for listening, and we'll see you next week.